Good morning, everyone, and welcome to the WST Time Domain Working Group series. I'm pleased to introduce Professor Anupam Bharadwaj, Assistant Professor at UCA in Pune, India. He earned his PhD from the University of Delhi, with part of his research conducted at the European Southern Observatory in Germany. He has held the research fellowships in China, Korea, and Italy as a part of the Mercury Fellow. His research focuses on stellar pulsation, time domain astronomy, precision cosmology, and he's been recognized with prestigious honors, including the Yahoo's Gruber Fellowship and the Divine Bappu Gold Medal. Joining me in welcoming Professor Anupam Bharadwaj. Anupam, thank you for being with us today. The floor is yours.
Thank you, Julia and Fatima, especially for accommodating me after the technical issues last time. So I will be talking about stellar astrophysics and how we can use it to probe the rate of cosmic expansion, that is to determine the Hubble constant. So this talk will be a more science focused because of teaching responsibilities. I couldn't accommodate a lot of WST aspects that are possible, but I think those we can explore. So when I say Hubble constant, we want to measure it using direct observations in the late universe. And for that, we need an image like this in the background. So this is a HST JWST color composite image of NGC 5468. It's a galaxy at 130 million light years from us, and it has one type 1a supernovae and more than 100 Cepheids. And that these two standard candles allow us to measure the Hubble constant. But what is the motivation? So the motivation comes from cosmology. We know that the early universe observations, such as cosmic microwave background observations, combined with lambda CDM model, gives constraints on key cosmological parameters, including, for example, the constituent of the universe. So we know that the dark energy is the most dominant constituent. And the matter that we see, stars, galaxies, is ordinary matter is only 5%. So with this model-dependent approach, we get a Hubble constant value that is of the order of 67.5 plus minus 0.5 kilometer per second per megaparsec. So this is a very precise sub-percent measurement of the Hubble constant. So why do we want to measure this Hubble constant in the local universe? So one motivation comes from this plot on the right, which shows how well you can constrain the equation state of the dark energy given the improvement in the precision of the Hubble constant. So if we can measure the Hubble constant to precisions better than 1% with the next generation of the CMB surveys or measurements, we can constrain the equation of state of the dark energy with similar precisions. So that means we can better understand the nature of the dark energy. For example, if it is time dependent or not. Unfortunately, as recently CMB S4 is no longer funded as much as I know, but of course we can expect similar programs in near future. At the same time, you can also combine local Hubble constant measurements with early universe probes in what is called combining the constraints to quantify or to constrain the matter density in the universe. So high precision local H0 measurements are very, very important. How do we measure these Hubble constants? So this is done with a stepwise distance ladder, which is nothing but a use of different distance indicators to reach farther and farther distances in the universe to eventually reach the Hubble flow, where the galaxies are moving away purely due to the expansion of the universe, and we can measure the Hubble constant. So in this step, you can look at different boxes, and at the bottom of these boxes are something called RR Lyrays and Cepheids. And these are primary stellar standard candles in astronomy. These are the stars that I am interested in. They are located in what is called the instability strip in the HR diagram. You can see these nearly two dashed vertical lines. And these instability strip contains Cepheids, classical and type 1, type 2 Cepheids, anomalous Cepheids, RR Lyrae variables. And these stars pulsate. They expand and contract periodically due to variations in the opacity and temperatures. and give a regular light curve variation from where you can get a period luminosity relation, which makes these stars very important distance indicators. I will be focusing on later half of this talk on MIRAs, which are late AGB stars at their latest stages of stellar evolution. And they also show similar period luminosity relations that we can use for distance measurements. So the most precise distance ladder that we have currently is using Cepheids and Type 1a supernovae, where in the first step you use Cepheids in your own galaxy or in nearby galaxy to calibrate their period luminosity relation using the geometric distances, which then in the second step is used to calibrate to measure the distances to Type 1a supernovae host galaxies and calibrate their peak luminosity of Type 1a supernovae. And then in the third step, you can go into the Hubble flow, use magnitude redshift relation for the supernovae to determine the Hubble constant. And this approach from the SHOES team, we get a value of H naught that is 73.2 plus minus 0.9, which is somewhere around 1.3% precise. And if we remember the value from the first slide that I showed, there is a discord of around 5 sigma between these two measurements that are coming from early universe and late universe probes. And this Hubble tension suggests that the universe is expanding faster than the predictions of the cosmological model. So there is some, if this problem persists, there is some missing physics in our understanding of the cosmological model. So given these states, it is very important to constrain what are these measurements based on Cepheid, supernovae, and other kind of distance indicators are anyway affected by systematic uncertainties. So you can do different analysis variants of the distance ladder, looking at different kinds of Cepheid samples, including all possible variations of known and unknown sources of systematic uncertainties. But the major takeaway is that there is no single source of uncertainty that can cause H naught to come below 72 or above 74. So I'll not have time to discuss all of these possible systematics. Most of those highlighted in bold font are related to stars, but I will focus on metallicity term or the metallicity dependence on Cepheid luminosities in the distance ladder. So this is an important problem to understand because the basic assumption of the distance ladder is that the Cepheid period luminosity relations are universal. So we can ask, does the metallicity effect on Cepheid period luminosity relation, which actually is a free parameter in the Hubble constant solution, can it bias distance estimates anyway, and it might lead to the Hubble tension that we see? And this is an important question because we know that the metallicity of Cepheids have direct implications for Hubble constant determination. So you can see on the plot on the left, the x-axis shows this metallicity coefficient and y-axis shows the Hubble constant. And if you consider just only the Milky Way solution, you can see that the contours are slightly sloped. So if you have a larger value of metallicity coefficient in the absolute sense, you get a smaller value of H naught. Of course, the Milky Way is not the only solution because you have 3 anchor galaxies. So if you look at the dark gray contour, which is the baseline solution, which is nearly flat, which suggests that if you have enough anchors with different metallicities, then your H naught estimates are somewhat insensitive to what this metallicity effect is on the Cepheid luminosity scales. But this is also predicted from the models from Julia and others that the topology of the instability strip changes depending on the composition, which in turn should lead to the variation in the slope and 0 point of period luminosity relations as a function of metallicity. So how do we measure this metallicity? So there are two different methods. The first one involves comparing intercepts of Cepheid period luminosity relations in nearby galaxies and plotting them as a function of the mean metallicity of Cepheids in those galaxies. And the slope of this relation will give you the metallicity coefficient. So this is the traditional approach that is also used in the SHOES project. But thanks to Gaia space mission and the parallaxes that we get from Gaia, for our galactic Cepheid samples, for which we can also do very high resolution spectroscopy, so we can determine their metallicities. we can do a period luminosity metallicity relation. So we can solve for the metallicity term using the information for the individual Cepheids. So this is exactly what we did for 75 Milky Way Cepheids with HST photometry that were used in the SHOES project. So these are shown in the gray data points here. And you can see that they show larger scatter than the red data points that are cluster Cepheids, which cover a narrower range in the metallicity. So we obtained high resolution spectra using esperons at CFST, and we put it in the Hubble constant solution. And what we found out is that there is not much of variation in Hubble constant, only of the order of 0.2 kilometer per second per megaparsec, depending on the individual metallicities or different metallicity scales of Cepheids that one can use in the Hubble constant solution. So this is a good result. But if you look at the metallicity coefficient, that is 0.21 plus minus 0.05. So this is not very well constrained. So there is still 25% uncertainty on this parameter. So we can ask, can we use information of Cepheids in our galaxy? So we have thousands of Cepheids in our galaxy now with Gaia and other surveys, for which we can do high resolution spectroscopy. We can get parallaxes for a large number of those. So we can ask, can we use metallicity coefficient at high enough accuracy and fidelity using Milky Way Cepheids so that we can use it as a prior in the Hubble constant solution rather than solving for it as a free parameter. So this is what is the goal of Cepheid metallicity in the Leavitt law surveys led by Vincenzo Ripepi at Embodiment Observatory. And on the left, you can see that we have a large sample of Cepheids that are being observed with different telescopes. And on the right, that at the same time, you want to do homogeneous multiband photometric light curves to get their mean magnitudes. So if you use these kind of samples, this is one of the results from one of the works from these surveys. You can see that you get two different sets of metallicity coefficients depending on the two different methods of determining it that I discussed earlier in the slides. So if you use the Gaia individual parallaxes and metallicities, you get a systematically higher value of the metallicity coefficient. If you use the 0 points of different galaxies, period luminosity relation, you get a lower value of the metallicity coefficient. So unfortunately, the uncertainties on these coefficients are still large enough to say anything conclusively, but this is something that needs to be explored. And with WST's MOS, I was reading that it can cover more than almost all of the Cepheids in the Magellanic Cloud. So that will also give us possibility to extend these analysis to nearby galaxies in near future. So in the second half of this talk, I want to focus on MIRAs because MIRAs are also very important stellar standard candles. These are very bright in infrared. They have very long periods and quasi-periodic light curves. So basically, if you compare a 230-day MIRA period luminosity relation, their infrared luminosity is equivalent to a 50-day Cepheid period, and 50-day Cepheid is slightly higher on the period side, while 230-day MIRA is somewhat in the lower side. So you can expect brighter MIRAs in infrared. That is the conclusion. But of course, there are also issues. MIRAs undergo circumstellar extinction because they have extended atmospheres, they have mass loss, and but there are also positive side because these stars are present in older populations. So you can find in all types of galaxies, not necessarily the young star forming galaxies where you find Cepheids. And then you can also find these stars in halos and less extincted regions of the galaxies. So MIRAs have very interesting properties. If we look at MIRA spectra as a function of pulsation phase, so at the maximum light, they show strong hydrogen emission lines, and at longer wavelengths, they show these TIO absorptions, which become smaller and smaller at brightest epochs when the star is very bright. So few years back, we wanted to explore these properties of phase-dependent properties of MIRAs. So we started looking at MIRAs from the Ogle survey, which provided decade-long light curves of these stars. So you have to model the light curves to get the maximum light luminosity, which we defined as the brightest 10% of the light. And then you can look at the period luminosity relations at the maximum light, minimum light, and mean light. What on the right shows the variation mean light. There is a significant reduction in sigma, which is the scatter in these relations. So these relations become tighter if you observe them at the maximum light. And this is useful because then you can use optical light curves of these stars, for example, from upcoming LSST, to also do a very precise period luminosity relations, which in turn allows you to measure the distances. So we were able to get relative distances between Magellanic clouds with similar accuracy, whether you use optical light curves at maximum light or infrared light curves at mean light. And this is an important result. As I said, this then allows you to use also the optical photometric data. But what happens at the maximum light? This result comes because there is a formation of unstable molecules in the extended atmospheres of MIRAS that happens at the minimum light, but these unstable molecules get destructed at the maximum light due to heavier temperatures. So at the maximum light, you can actually probe the visual luminosities of the stars by going through the extended atmospheres. But as the stars approaches minimum light, there is a formation of unstable molecules like titanium oxide, water molecules, which form up to 1.8 stellar radii. That means you cannot see the intrinsic or the visual light of the stars coming from its center. But of course, then this can be mitigated somewhat if you go to the infrared, because then that allows you to go through the dust in their extended atmospheres. So more recently, we started looking at MIRAS in global clusters. This is because the idea was that the cluster MIRAS can actually provide you a better calibration than the field MIRAS, because for the field MIRAS, these are very bright point sources, and they're due to chromosity and other issues, it's difficult to measure their parallaxes. But on the other hand, if you go to clusters, you can use other kind of stars in the clusters to determine their parallaxes and distances. So this was the idea, and for this you need a sample of MIRAS that are in the globular clusters, and you have to monitor them in the infrared, because as I said, you want to measure them in the infrared to have tighter and tighter period luminosity relations, and also lesser effects of circumstellar and interstellar extinction. So we observed around 55 long period variables in 18 globular clusters. You can see some nice light curves of these variables. They are all observed with a very small 1 meter class Sirius IRSF telescope at South African Astronomical Observatory. We have MIRAS covering a wide range of periods, but you want to identify the MIRAS that are members of the clusters, and as well as the MIRAS that show surface chemistry of being oxygen rich, because the oxygen rich ones are the ones that follow a tight period luminosity relation. So for this, you look at different properties, you look at proper motions, you look at their spatial distributions, their long period variability information, location on the optical infrared color magnitude diagrams, and then you select MIRAS that are actually the members of the cluster. So for example, in the top, this is NGC 6441. You can see V25 is somewhat an outlier in most of the planes. And this is actually not a member of the clusters. On the other hand, for NGC 104, most of the stars are members of the clusters. The proper motion information is not very reliable, because most of these clusters are in the bulge, and then there is a significant extinction and crowding, which limits the measurement of proper motions accuracy for these stars. Nevertheless, we were able to find out using different selection criteria. For example, by comparing the proper motions of the individual stars with the proper motions, mean proper motions of their host clusters, looking at what the variability amplitudes of these stars are, look at their positions in the color magnitude diagram and color diagram, we were able to select the stars that are most likely cluster members and that are most likely oxygen-rich stars. Of course, this will be easier having a spectroscopic follow-up, because then you can measure the specific molecular bands in the spectra of these cool stars, for example, using WST. So you can actually identify which ones are carbon rich and which ones are oxygen rich. Of course, for now, we did only the photometric classification. And then you can look at the period luminosity relations of these stars. So as you can see, the period luminosity relations for these 41 stars that we found as candidate clusters, candidate members of the clusters, it shows a very nice period luminosity relation with a scatter of typically 0.15, which is also what we find for Miras in the Large Magellanic Cloud. So this is something that we believe is intrinsic to Mira population. And we also find that the relation was somewhat in agreement with the LMC relations. So this included accurate mean light curve, mean magnitudes from the light curves, distances and parallaxes from these catalogs. We used reddening and of course metallicities for the individual stars. So this is a paper that is appearing on arXiv tomorrow. So I think it's good that we are having this talk today. Then we transformed, because we want to use these relations to determine the Hubble constant. So we transformed the ground-based H-band to HSTF 160W filter, because this is what is used to measure extragalactic Miras in supernovae host galaxies. Then we derived this period luminosity relation in this HST filter, and the bottom panels show the residuals as a function of period, metallicity, reddening. You can see there's not much of trend, especially for the metallicity. So you can assume that these cluster Miras do not actually show any significant metallicity dependence on their period luminosity relation. And then we used what is similar to CIFIDS, a 3-anchor baseline calibration for the first time. You can put the calibration that is based on galactic stars, in this case, cluster stars. We also used some Milky Way field stars, which we do not use in the calibration because of issues with their parallaxes, of course. But with these 3 anchors that are exactly similar to the CIFID case, you can get a very precise absolute 0 point of a Mira of 200 days, and what will be the metallicity effect on its luminosity. So we used these 3 anchors for the independent calibration of the distance ladder, and then combined them to measure distances to 2 type 1a supernovae host galaxies that have known Miras to date. And then eventually you can use that to determine the Hubble constant. So we provided the most precise 3.7% measurement of Hubble constant based on Miras, and the value comes out to be 73.1 plus minus 2.7 kilometer per second per megaparsec. And this is very in very good agreement, actually within 0.1 sigma to CIFID based Hubble constant determination. Of course, the uncertainties on this measurement are still much higher, at least three times larger than those for CIFID supernovae distance ladder. And this happens because we have only 2 supernovae host galaxies with known Miras. In terms of the calibration at the first step, we are almost at a similar precision to CIFIDS, because now we have 3 anchors galaxies. And this is also important because with LSST, we have already seen the first images. We'll have a number of Miras in extragalactic systems that we can utilize for distance measurements and building a Mira-based distance ladder. So to conclude, we know that there's an ongoing tension in the Hubble constant measurements. If we look at CIFID supernovae distance ladder, which is the most precise one, small systematic uncertainties like metallicity effects that do not impact the local Hubble constant measurement significantly. But of course, it is important to quantify this metallicity effect precisely if we want to achieve percent level precision on these measurements. Miras provide an excellent alternative to CIFIDS to determine the Hubble constant, and we provided a new anchor to calibrate Hubble constant using globular clusters. And we find that this Hubble constant value is in very good agreement with secret supernovae-based determinations. Of course, the uncertainties are larger, but something that we can reduce by observing Miras in supernovae host galaxies, many of which I expect will be observed with LSST. Okay, thank you.
Thank you, Anupam, for this very interesting talk and for sharing this paper on Miras with us that I think will have a big impact on the community. It's time for questions and discussion. I have a fair question for now. How far you can go with Miras?
So with Miras, you can, the intrinsic magnitudes around similar to 10 decibels. So you can easily go up to 20, 30 megaparsec with HST.
Okay, right.
Yeah,
And what would really be the impact of next Gaia releases on both the first step? It is supposed to have parallaxes with the precision less than 5 microarcsec, no?
Yes.
Do you think
The
that
problem
you
with
can have a real impact on the list of the H0 determination and the impact of next Gaia data releases on Miras, since you are studying?
Yes, so we looked at field Miras. Actually, I have not shown them here. The problem is right now, let's say if I say the average uncertainty on cluster is around 1.4%, for field Miras, it's 6%. So it doesn't contribute a lot. And then there is an additional parallax 0 point offset that needs to be taken care of. The problem with the Miras is that, as I said, these stars have extended atmospheres. So for the stars that are closer to us, where we can do very precise parallaxes, they are not exactly, let's say, point sources, right? So it's difficult to do their astrometry. But I believe that with the next or with the upcoming Gaia data release, there are possibilities to take into account chromaticity corrections, due to colors and amplitude variability of these stars, which might help improve the precision of parallaxes for especially these long period variables, long amplitude, large amplitude, long period variables. But still, I would be a bit skeptical about getting field Miras calibrated to let's say 2% or better. But still, if it is 2%, then you have a cluster which is somewhere around 1.2%. You can have a comparative analysis and get a better constraint as an additional anchor to calibrate the peak luminosity, the absolute luminosity of Miras.
Okay, thank you, Anupam. Questions from the audience for Anupam? Just a sec. Okay. I think that we can conclude the session here. Thank you, Anupam, for being with us today and this very interesting talk that we can read the paper tomorrow. And
perfect time.
Yeah, this seminar marks our last session before the summer break, and we will resume on September 9 with a talk by Yaroslav Mark. Have a great day, anyone, and thank you, Anupam, again for the talk.
Thank you.
Bye.